Alright, welcome back. In this video, we're going to go over gluconeogenesis, the intro, and steps 1 and 2. I know, right? It's just another pathway. It never ends. So if you're new to this channel, I like to go over pathways in a way that makes it super easy for you to remember it, but also really detailed, and we go through it slowly, because these are challenging concepts. And my job is to make sure you're not confused when you go to your midterms. So let's do this. Gluconeogenesis is the process that converts pyruvate back into glucose. It's the opposite of glycolysis. Because glycolysis was taking glucose and turning it into pyruvate, where gluconeogenesis is taking that pyruvate and turning it back into glucose. So it's the reverse. The steps are actually fairly similar. There are a few differences, especially in the earlier steps, but as we go on, it gets basically similar and similar. And I want to be honest with you guys. This tends to be everyone's least favorite subject. It's even my least favorite. I'm not going to lie to you guys. I hate it. The reason is because a lot of people don't realize the importance of gluconeogenesis. That, or they just finish glycolysis, they're like, oh my god, another pathway? I can't do another one. Well, spoiler alert, there's probably going to be like 4 more pathways after this, so it doesn't end. But no fear, I will make it easy. Now, what is the purpose of gluconeogenesis? If glycolysis makes energy, and gluconeogenesis just uses energy, it sounds pointless. Why do we want to use energy? It doesn't sound efficient at all. Let me break it down for you so you really understand. Say you're doing a marathon, for example, and you're low in glucose. Your blood glucose levels are low. We're going to undergo gluconeogenesis, creating pyruvate and going back to glucose. And creating glucose, now we have high glucose levels in our blood. But why is this important? When you have low glucose levels, your brain is not working as it should. It actually needs glucose to survive. It cannot really operate well under low glucose levels. This is why people who are tired can't really think as well. They don't have, how should I describe it? It's kind of like a brain fog. Think about it like that. When they're tired, they can't think straight. Well, it's usually due to low glucose levels. So we're going to produce glucose and shove it into the brain so we can actually start thinking clearly. Because your brain, funny enough, is actually really smart. It tries to protect itself at all costs. And this is one of the methods. It's going to sacrifice pyruvate. Because your body knows we can use pyruvate, go through the Krebs cycle, go through the ETC and generate ATP. But your brain is smarter than that. It's like, no, I need to prioritize myself right now. And I think it's best to get glucose up to the brain so we can function better. And that's why we're doing this. So let's do it. Step 1. Here's what we're going to do. We're going to have pyruvate, because that's what we're starting with. And we're going to have the enzyme pyruvate carboxylase. And we're going to create oxaloacetate. So this requires ATP and bicarbonate. The ATP is going to basically break off into ADP plus P, and it's going to push this reaction forward. Notice that this is irreversible. Once we go from pyruvate to oxaloacetate, there is no going back. So this ATP breaking off is going to basically pull this reaction forward so we can actually do the reaction. But this bicarbonate is actually super, super, super important. But before we get into that, using pyruvate carboxylase, we're going to add a carboxylate group to carbon 3. So this bicarbonate is going to basically break off, and we're going to add a carboxylate group to carbon number 3. And it's going to create a 4th carbon. Because this is carbon number 1, carbon number 2, carbon number 3. It's carbon 1, 2, and 3. And we're going to add a carboxylate group here to carbon number 3, creating a 4th carbon. Now here's something really important that I need you to memorize. You need to know all of this, but this is something you really need to know, especially for biochemistry. And if you're going to take the MCAT as well. Bicarbonate is a buffer in our body. It is participating in the reaction directly because it's going to basically provide the carboxylate group, but it also makes sure the pH is correctly balanced so this enzyme can do its job. This reaction is so important that we must make sure at all costs this enzyme is happy and working, because enzymes work at particular pHs. We need to make sure the pH is correct. And how does it do that? Well, I'll make a whole video on the buffering system. But for example, if our blood is too acidic, bicarbonate is going to bind to a hydrogen ion, because hydrogen ions tend to be acidic and cause blood to be acidic, and it's going to create carbonic acid and basically neutralizes the pH. So to sum up, what we're doing here is first, we're taking the pyruvate. And notice that we have a CH3 here. We're going to turn this into a CH2. Okay? Then we're going to add a carboxylate group to carbon number 3. And this will create carbon number 4. Right here. And this uses ATP and bicarbonate. Alright, step 2. Step 2 tends to be a little tricky for people to understand. So let's take it slow. Here's what we're going to do. This oxaloacetate, we're actually going to break it off. And you're probably wondering, wait a second, we just added it here. Why do we just break it off? And I'll get to it. But here's what we're going to do. We're going to use the enzyme phosphoenol pyruvate carboxykinase. It's a long word. And we're going to take a GTP molecule. A GTP molecule is like an ATP molecule, but instead of adenine, it's guanine. And we're going to break off a phosphate group because we go from GTP to GDP. Triphosphate to diphosphate. So we have now stripped a phosphate group off. And we're going to add it to this oxygen here. So this oxygen was in a double bond. We're going to break that double bond and make a single bond to the phosphate group. That's the first thing it's going to do. The second thing that we're going to do is we're going to take this carboxylate group and break it off, shred it off, and to become CO2. The CO2 is what we breathe out. This CO2, well, rather, I should say the carboxylate ion or carboxylate group we just broke off, you're probably wondering, why did we just do this? This seems so pointless just to add it and take it off. Well, actually, there's a really good reason why we did this. The reason we need to do this is because we need to make sure that we can break this double bond and make a single bond, but also create a double bond between the C carbon and CH2 here. Because remember, we had a CH3 in the beginning that was a single bond. Then we added the carboxylate group, and now we're left with a CH2 and a double bond. So from a CH3 to a CH3 with a single bond, which is pyruvate, we now have a CH2 with a double bond. And the only way this could happen is if you were to shred this off. So, once again, why we're doing this is we take this, we shred it off. Now, carbon, so let's shred all of this off. Now, the CH2 has 3 bonds. 1 and then 2 from the hydrogens. So we're going to instead create a double bond here. That's what we're doing. Because the carbon cannot have 3 bonds, it must have 4 bonds. And that's why we're doing this. So to really sum up, we're shredding this off, making a double bond between the carbon and the CH2, and adding a phosphate group to the oxygen in exchange for a double bond to a single bond. And that's it. I mean, it's not the end of gluconeogenesis. I'll still do steps 3, 4, 5, and 6, and so on. But I just wanted to do the first 2 steps so you kind of get a grip of what we're doing. So if you found this video helpful, please like and subscribe. Until next time, later.